Hesameddin from Purdue University. He will talk about 2D tunnel transistor for ultra-low power applications.
Hello everyone, my name is Hesam from Purdue University. I'm going to talk about 2D tunnel FETs. And this work is funded by LIST. So the outline of my talk is that I'm going to motivate the 2D tunnel FETs, and I'm going to talk about challenges and on-current challenge and scaling challenge of these tunnel FETs. So what is the motivation for these 2D tunnel FETs? As you know, over the years, we increased the frequency of the CPUs, and as a result, we increased the power. It was not a problem until we reached 10 years ago to the cooling limit, which is around 100 watt per centimeter square. And from that time till now, we couldn't increase the frequency. And this is a big challenge for electronic industry. So let's go to a device, a switch, and see what is the ideal switch for less power consumption. As you know, that this is a conventional MOSFET. We have off current, on current, and 60 millivolts per decade. So what would be the ideal case? The ideal case would be we have very high on current, and we can also reduce the supply voltage, but also we have a very a small off current and very steep device. But all of these aspects are challenges for any device like tunnel FET. But I'm going to focus on just high on current and a scaling challenge. So if we compare MOSFET and tunnel FETs usually have a steeper IV because there is no hot carrier. Since the hot carriers, for hot carriers there is no state, it's inside the bandgap. But what is the challenge for tunnel FET? It's in the on current, you need to tunnel through, so the tunneling transmission is not high. As a result, you see that the on current of TFET is less than MOSFET. So how we can solve this on current problem? This is here I'm showing the scaling length, which determines how sharp is the potential profile. This scaling length is kind of related to tunneling distance, and it is known for 20 years that if we decrease the channel thickness, this scaling length would be smaller. So let's compare a thick channel versus a thin channel tunnel FET. In the thin channel tunnel FET, this tunneling distance we expect to be smaller, and the on current we expect to be higher. So and that was the motivation. That's why we are looking for 2D tunnel FETs. But let's look at the atomistic data that we have. So for 2D material, we chose transition metal like chalcogenide. Professor Jabi talked about them. The good point is that we can exfoliate them in the lab very easily, and they have the best electrostatic gate control. But the main questions that we had was that what is the performance of these TMD tunnel FETs? So this is the result that we got, and we find out that actually thin channel is not enough for high performance, and we need to have a good channel material. What is a good channel material? A good channel material is a material with a band gap around 0.7 and a low effective mass, but that's not all. You know, we need to have a good design we need to have very high doping and very small oxide thickness to get high performance 2D tunnel FET. But let's see why we couldn't achieve very high performance in 2D tunnel FETs. I talked about this lambda, and we could make it very small, like 0.4 nanometer. But since we have a depletion region in the source, you would see that even with highest doping, like 1E20, we would have a 2-3 nanometer still depletion width. So the whole tunneling distance wouldn't be very small. So we thought that, okay, a simple solution would be that we make electrostatically doping. So we make two gates with different biases, and we made this PN junction. And we hope that both of them had like 0.4 nanometer distance. But what happens, actually we explained the details here, but after all, we find out that actually when we do electrical doping, this lambda increased to 1.5 nanometer. And this was strange for us. we looked into the data and we saw that, okay, actually this comes from the fringing field when we have 2 gates. Even if you put a 0 distance between these 2 gates, there would be some fringing field. And this fringing field is somehow proportional to oxide thickness. So you cannot, since you have gate leakage, we cannot make the oxide thickness very small. So we cannot reduce this tunneling distance. So let's again review the problem. We talked about this depletion widths in the chemically doped devices. We tried to make 2 gates and make this p-n junction, but this lambda has changed. So is there a way to solve this problem and make this tunneling distance smaller so we can get high on current? What we did is very simple idea that we put a low K material between these 2 gate region. So how come this combination of low K and high K would help? We know that the displacement field should be continuous in the interface. So if we reduce a dielectric constant, the electric field would increase. And this is a very simple way to amplify electric field. And this is right on top of the tunnel junction, so our on current would increase. So let's look at the atomistic simulation result. You can see that we can achieve very high electric field with this simple method. And we can also get a very good subthreshold swing and on current. We have a patent application, and this paper is actually published recently in EDL. But I talked about the on current challenge of tunnel FETs, but there is another challenge it is a scaling challenge. So let me first start with the scaling challenge of MOSFET. And so when we make the channel length of MOSFET shorter and shorter, you would see that the optimum effective mass increases. And this is due to the fact that we have source to drain tunneling. And this is a bit strange, but we should look actually for low mobility materials for future transistors because of this source to drain tunneling. So, but what about sub-10 nanometer tunnel FETs? I mean, what kind of material is good for those tunnel FETs? Let me remind you about our goal. We wanted to be able to reduce this VDD and obtain low power. But what happens in reality when we decrease the VDD and channel length in a tunnel FET? You would see that the IV, somehow the performance gets destroyed. Why this happens? The reason is that if you look into the on current is proportional to tunneling energy window. And since we are reducing the VDD, we are reducing the on current. On the other hand, we have this direct source to drain tunneling, and that's increase the off current. So how we can solve this problem? There is, I mean, you can see that we expected, actually we worked on tunnel FET to go to these voltages and dimensions, but the performance, there is no performance in those dimensions. So what we tried to do, we tried different cases. Here you can see a IV for effective mass MS star and band gap EG. Once we reduce the band gap and increase the effective mass, you can see the IV gets much better. But in the other case, we increase the band gap and reduce the effective mass. You can see that it gets worse. So what we concluded is that actually when we are doing the scaling in tunnel FETs, we need to reduce the band gap and increase the effective mass. But this is not enough just to reduce and increase this. We need to go to an optimum space. So you can see as we decrease the VDD, we need to go to higher effective mass, but there is an optimum space for effective mass. So if we use this knowledge and try to design a tunnel FET based on this MS star and EG, we would see that we can still scale the devices pretty well. So to summarize my talk, regarding the channel material requirements that we have for successful scaling, in case of MOSFET, we need to go to higher effective mass and higher band gap. So in this regard, something like MOS2 is pretty good because it has large band gap and large effective mass. So it is shown that it can actually go to 5 nanometer and it still works pretty well. So in this regard, 2D MOSFETs are pretty good for future MOSFET application. But how about the tunnel FETs? In case of tunnel FETs, it's a bit more strange that we need to go to higher effective mass, but lower band gap. And you can see the band gap, actually the best band gap is around 20% above the VDD value. So if you are talking about 0.5 volt, the best band gap is around 0.6 electron volt. But we need to remember that we always need to go to the optimum point in these materials. So again, these 2D materials are good because they usually have a high effective mass, and you can, with thickness control, you can achieve different band gaps in these materials. So I would like actually to thank my advisor, Professor Kilemek, and the experimental groups that we are working on. And these are my colleagues, and I would like to thank all of you for your attention. Thanks.
Okay, thank you very much. I think we have 2 questions. All right.
Can you explain physically why I would want a higher effective mass?
For tunnel FET or
For the tunnel FET, you want a higher effective mass. Why?
Oh, let me see if I have the slide here. Yeah, so you can see actually increasing effective mass or just band gap have similar effect. They decrease the off current, yeah, both. But the point is that—
So you're saying it's a struggle for off current?
Yes, but I want to say that you see the off current decrease when I decrease band gap or increase the band gap or increase the effective mass. Both have a smaller off current. Yeah, transmission is smaller. But the point is that when I increase the band gap, I need to spend more voltage to go to that lower off current. Yeah, because it is like EG half. We need to go to EG half. But in the case of effective mass, we don't need to because we didn't increase the band gap. You know, so that's the benefit of increasing band gap.
All right, one more question.
Typically, the mass and the band gap are linked. If you look at bulk 3.5s, for example, it's about the mass is 1/20th of the band gap. So how do you have some ideas about how to design to get whatever mass you want?
That's actually a very good question, and it was our concern too, because what we are saying is that it is the opposite direction. That we are saying that we need to go to higher effective mass and lower band gap. So it's a bit hard to achieve in one material. But you know, there are 2D materials that still can have these properties. You know, so in different nodes, we need to look for different 2D materials. It is somehow the idea. So we cannot use one material and just scale it.
All right. I think let's. Okay, very quick question then. Go ahead.
I had a question in your in the 2-gate design. How close are those 2 gates together, and how much voltage are you expecting to put across there? Essentially, I'm asking, wouldn't you expect your gates to leak to each other very heavily?
Yeah, that's a very good question. Actually, we explained this point in the paper too, that this distance can vary from 3 nanometer to 1 nanometer. You know, this is in that order, but it can be air gap. You know? So the air gap doesn't and if we calculate the gate leakage, it is still in good level. And we are talking about low VDD, so the difference between voltage is not that high.
But you need to bend the entire band.
Yeah, but you can do that in using like work function engineering. Yeah, so not the whole metal would see the voltage. Yeah, it's like the work function engineering.
Okay, thank you. I think let's speak again. Thanks so much.